everyone. Today I'm going to tackle about the role of enzymes in metabolism and disease. Today I'm going to discuss all about enzyme, its function and regulations in human health, including disorders caused by enzyme deficiency. We all know that enzyme is an essential catalysis. This presentation will explore the world of enzymes, the microscopic powerhouses that make life possible. We'll cover their fundamental role, how they're controlled, and what happens when they don't work correctly, leading to disease. What are enzymes? They speed up biological reactions within our body, often by millions or billions of times without being used by themselves. Think of them as molecular accelerators. It works by lowering activation energy, making reaction happen much faster. They provide an easier path for reaction to proceed. Highly specific. Each enzyme typically acts on a particular molecule called a substrate. It is a specialized binding region known as the active site. This is often described by the induced pit model, where the enzyme slightly changes shape to perfectly embrace the substrate. Without enzyme, most of our body's essential reaction would occur too slowly to sustain life. They are like specialized tools, each designed for one specific job. How enzymes work and what affects them. Enzymes create a favorable environment for reactions, stabilizing the transition state. This unstable, high-energy intermediate state is made easier to achieve by the enzyme. Enzyme activity is sensitive to environmental factors such as temperature, pH range, substrate concentration, and the coenzyme or cofactors. In temperature, there's an optimal temperature around 37 C in human. Too low, reaction slow down. Too high, the enzyme permanently loses its shape and functions, or the so-called denaturation. pH range. Each enzyme has an optimal pH range. Example, stomach enzymes prepare acidic pH, while intestinal enzymes prepare alkaline. Extreme pH causes denaturation. Substrate concentration. As substrate increases, reaction rate increases until all enzyme active sites are busy or saturation. Cofactors or coenzymes. These are helper molecules like metal ions or vitamins, often needed for the enzyme to function properly. Enzymes are specialized protein or sometimes RNA molecules that act as biochemical catalysis, significantly speeding up chemical reaction within living organisms without being used up themselves. They achieve this by lowering the activation energy, the initial energy required for a reaction to happen. How does enzyme work? Each enzyme typically has a unique three-dimension shape with a specific region called the active site. This active site is designed to bind only to certain reactant molecules known as substrate, much like a lock and key. Enzyme substrate complex. When the correct substrate bind to the active site, an enzyme substrate complex is formed. This binding brings the reactions together and often puts a strain on their bonds, facilitating the chemical transformation. Once the reaction occurs, the enzyme converts the substrates into products, which are then released from the active site. The enzyme is then free to catalyze the same reaction again with new substrate molecules. Several factors can influence how effectively enzymes function, which are the temperature, pH range, substrate concentration, and the cofactors or coenzymes, and the inhibitors or activators. These factors are important for maintaining enzyme efficiency. Imagine a machine that only works perfectly within certain environmental conditions. Enzymes are similar, and understanding these limits is vital in medicine and industry. Enzyme regulation and processes, keeping things balanced. Crucial for maintaining metabolic balance and responding to cellular needs, our cells need to turn metabolic pathways on or off, or speed them up or slow them down, depending on depending on energy demands or nutrient availability. The methods includes allosteric regulation, covalent modification, and gene expression. Allosteric regulation is a process that molecules bind to a site other than the active site, causing a conformational change that either activates or inhibits the enzyme. This is a rapid on or off switch. Covalent modification includes chemical groups like phosphate groups are added to or removed from the enzyme, often by other enzymes. This is a common way cells respond to signals. Example of that is hormones. In gene expression, the cell controls how much of an enzyme is made or synthesized or broken down. This is a slower, long-term regulatory mechanism. Enzyme regulation is like a sophisticated feedback system in a factory. If too much product is made, the system slows production. If resources are scarce, it might prioritize different pathways. Enzyme and metabolism, the core of life. Enzymes drive all metabolic processes, the sum of all chemical reactions in the body. Facilitate anabolism, the building up complex molecules requiring energy, and catabolism, the breaking down complex molecules releasing energy. Each step is in complex pathway, like glycolysis breaking down glucose for energy, or the Krebs cycle, a central energy producing cycle, is precisely catalyzed by a specific enzyme. Ensure efficient energy production and nutrient utilization, keeping our bodies functioning from the cellular level up. Our entire existence, from breathing to thinking, relies on thousands of interconnected enzymes catalyze reaction. They form the intricate biochemical machinery of life. Enzyme deficiency often inherit genetic disorders. These conditions result from a mutation in the gene that provides instruction for making a specific enzyme. A faulty gene leads to a missing or dysfunctional enzyme. The enzyme might not be produced at all, or it might be made incorrectly and can't perform its job. Consequences are substrate buildup. The molecule that the deficient enzyme is supposed to process accumulate to toxic level, causing damage to cells and tissues. Product deficiency. Essential molecules that the enzyme normally produces are lacking, disrupting vital functions. These deficiencies highlight the critical role of every single enzyme. A single broken enzyme can have cascading effects throughout the body, leading to serious health problems. The example of enzyme deficiency are phenylketonuria, or the PKU, or second one is lactose intolerance, third is the Tay-Sachs disease, the fourth is the Gaucher disease. What are they? Phenylketonuria, or the PKU, is the deficiency of phenylalanine hydroxylase that leads to toxic buildup of phenylalanine if untreated, causing severe intellectual disability. Managed by a strict low phenylalanine diet from birth, this was one of the first disorders detected by newborn screening. The second example of enzyme deficiency is the lactose intolerance, which is very common. This lactose intolerance is the deficiency of lactase. This enzyme breaks down lactose, or the milk sugar. Without it, lactose ferment in the gut, causing bloating, gas, and diarrhea, not typically life-threatening but very common. The third example of enzyme deficiency is the Tay-Sachs disease, which is the deficiency of hexosaminidase A. This enzyme is crucial for breaking down a specific lipid, the so-called GM2 ganglioside, in nerve cells. Its accumulation leads to progressive neurodegeneration, blindness, paralysis, and is typically fatal in early childhood. The third example is the Gaucher disease. Gaucher disease is an autosomal recessive disorder. It is a rare inherited genetic disorder where the body lacks sufficient amount of a specific enzyme called glucocerebrosidase, or the GBA. This enzyme is crucial for breaking down a fatty substance called glucocerebroside. These examples illustrate the diverse impact of enzyme deficiency, from manageable dietary conditions to severe life-limiting neurological disorder. Early diagnosis is important. Let's proceed to diagnosis, treatment, and enzymes as drug targets. Diagnosis. Newborn screening is crucial for early detection of many metabolic disorder, which is, for example, is the PKU. Enzyme assays, measuring the actual activity of an enzyme in blood or tissue samples. The third diagnosis is in genetic testing, identifying the specific mutation in the gene. Treatment, dietary modification, enzyme replacement therapy, or the ERT, and the gene therapy. Dietary modification, restricting the accumulation substrate. Example is the low phenylalanine diet for PKU. Enzyme replacement therapy, or the ERT, directly providing the missing enzyme intravenously. Example for some lysosomal storage disorders like Gaucher disease. Gene therapy is a cutting-edge approach aiming to introduce a functional copy of the faulty gene into the patient's cells. Enzyme as drug targets. Many medicines work by inhibiting specific enzymes involved in disease processes. Example is the statins inhibit an enzyme in cholesterol synthesis. ACE inhibitors lower blood pressure by blocking an enzyme. Our growing understanding of enzymes allows for powerful diagnostic tool and highly effective treatment, and provides molecular targets for drug development. In summary, enzymes are vital biological catalysts, absolutely essential for life's processes, regulating countless biochemical reactions. Their precise regulation maintains cellular and bodily health. Deficiencies or malfunctionings lead to a wide range of human disease. Understanding enzyme is key to modern medicine, from diagnostics and treatment of inherited disorders to the development of life-saving pharmaceutical drugs. Enzymes are the unsung heroes of our bodies, working tirelessly at the molecular level, making every biological reaction possible and unfeeling the very essential of our lives today. Thank you everyone for listening, and that's all for today.